Hello and welcome again to my Physics Online video lecture series. Today's video, I'm going to be talking about Newton's second law in rotational dynamics. In some sense, this is the first video in our rotational dynamics series, or in my rotational dynamics series of videos. So you should be, if you're watching these videos in order, you should be done with translational motion, including energy and momentum. And you should also have watched the videos on uniform circular motion, orbits, and the like. Those are kind of what form the backdrop to this. So this video, we could begin by recalling that we have translational motion, and now we also have rotational motion. So at this point, you should have watched already stuff about the rotational kinematics video. So you may want to review rotational kinematics before watching this. And of course, I have a series of videos that go into those. The one you specifically should watch is about the kinematics itself. So things like delta theta is equal to 1/2 alpha t squared plus omega naught t for constant alpha. That kind of stuff. There's also another one about tangential and centripetal motion, which you might also want to go review before watching this one. For translation, the equivalent to this equation would be delta x is 1/2 at squared plus v initial or v naught t, and this is constant acceleration. Okay, so you may want to refresh yourself on those. And then the other thing to note is that we've encountered Newton's laws. So Newton's laws govern translational motion, at least in their force form. In particular, we have that the sum of forces for an object whose mass isn't changing, the sum of forces is mass times acceleration. That is the second law. And we also have the first law, which we wrote the sum of forces equals 0 implies that acceleration equals 0, or really implies that change in momentum is 0, but we could say implies acceleration is 0. And then what makes this even more useful in the recall part of this is we can adapt it to rotational motion. And that the adaptation, along with the first law, basically gave us the two conditions for equilibrium, which you may recall. And so we had rotational equilibrium and we had translational equilibrium. Translational equilibrium went with sum of forces being 0. Rotational equilibrium went with sum of torques being 0. Now the reason why I bring this one up is because we can recall that this right here basically is governing things like the translation. It governs the acceleration, which then governs everything that depends on the acceleration. And this one right here gave us equilibrium, and then we adapted it by saying, well, torque also needs to be balanced for equilibrium. And so the question should be in your mind after having watched that video, what is it that happens if the torque is not balanced? So what if torque is not balanced? What would that imply? Well, it implies something very similar to Newton's second law, the sum of forces being mass times acceleration. So let's write that one down for starters. Sum of forces is mass times acceleration. For most objects, the mass isn't changing. If we switch this over to torques, we actually get a parallel equation. It says that the sum of torques on an object is equal to a moment of inertia times the angular acceleration. So this is basically Newton's second law as applied to rotations or to rotational dynamics. Now I will go into more detail about what this term right here represents. This is what's called moment of inertia. And I will discuss that in more detail in a future video. You could think of it in some sense as follows. The mass, often represented by an m, measures translational inertia. So the more mass an object has, the more force you have to apply to the object in order to get it accelerating with a given acceleration. Maybe you say, I want to accelerate some object by 1 meter per second squared. The more massive the object is, the more force you have to apply to achieve that 1 meter per second squared. Okay, that is the inertia of the object from a translational perspective. The moment of inertia, I, provides an analogous measure of an object's rotational inertia. So this is rotational inertia that we're measuring here. So what is the equivalent then? Well, in rotations, if you want to speed up an object's rotation, so I have like a wheel or some such thing like this, and I want to speed it up. Maybe it's moving about this axis of rotation here, and it's initially moving with omega, and I want it to speed up. So want to speed up, that implies that we will have some angular acceleration alpha. Maybe I want to speed up such that alpha is 1.0 radian per second squared, just as we had acceleration of 1.0 meter per second squared. Well, the more moment of inertia this object has, the more rotational inertia it has, the more torque I'm going to have to apply to make that happen. So I would have to apply a torque basically in this direction. This is the direction of tau, in order to get alpha to be in the direction that I'm wanting it to speed up in. So I want it to speed up. It's already rotating counterclockwise as viewed from this plane. Therefore, I need a counterclockwise torque that's equivalent to a torque that points up out of the screen at you. All right, so the more the moment of inertia is, the larger the moment of inertia for this wheel, the more torque I'm going to have to apply in that direction in order to achieve this 1 radian per second squared alpha. So what do you think plays into the moment of inertia? Well, I will unpack that, like I said, in a whole separate video. You should expect that the more massive the wheel is, the more torque I'm going to have to apply to get it moving. And you'd be right, but it's not just mass. It's also how the mass is distributed. In any case, we have a second law assuming a constant moment of inertia. So we'll say this is assumed constant for now. If it's not constant, then you'd have an I alpha plus an omega, the rotational speed, times the rate change of the moment of inertia. And it actually becomes easier in that case to talk in terms of a thing called angular momentum, which is also for another video. So let's work a quick example to wrap things up. So for our example, we have an object that has a moment of inertia of 12 kilograms dot meters squared, presumed about whatever axis of rotation it's going to be rotating about. We then apply a net torque. This says a net torque, if you can't read my weird handwriting. A net torque of 18 Newton meters is applied to this object about this axis of rotation for which this moment of inertia is specified. These are kind of some hints looking forward about what we may have to talk about in that other video. And this torque is applied for 3 seconds. And so assuming that the object's initially at rest, meaning not rotating, what angle will it rotate through in those 3 seconds? So a constant value of torque will give me a constant value of angular acceleration. And so my delta theta, the angle through which I have rotated, should look like 1/2 alpha times squared plus omega naught time. The object, it says, is initially at rest. So that's equivalent to saying omega 0 equals 0. So this term is 0. We need to solve for alpha in order to get delta theta. So this equation right here lets us solve for alpha. Specifically, alpha should look like the torque divided by the moment of inertia. So that is 18 Newton meters divided by 12 kilogram meters squared. And that will give me 1.5 radians per second. Therefore, delta theta should look like 1/2 of 1.5 radians per second times 3 seconds squared. And that, if my mental math is correct, should be 6.75 radians. So that's a little bit over 1 revolution that will have been completed in this time of 3 seconds. So that's all I have for today's video. Hopefully you've learned something from it. Hopefully this has been a nice introduction to this topic for you. And as always, thanks for watching.